Welcome to this lecture on combinatorics. In a previous lecture on the same topic, we discussed several fundamental rules of combinatorics and in particular counting problems, namely the sum rule, the product rule, and the principle of inclusion-exclusion that applies to two sets. In this lecture, we're going to discuss additional principles, rules, and formulas to solve counting problems. And in this segment, we're going to discuss the pigeonhole principle. So assume that n and k are two integers. The first version of the pigeonhole principle will be stated as theorem 1. So let's say you have n distinct objects, and these objects are to be placed into k distinct boxes, where n and k are not only integers, but they are positive integers, and n is greater than k. That's the crucial assumption here. So there are more objects than there are boxes. Then the theorem states that at least one box contains at least two objects. That is the simplest version of the pigeonhole principle. So how would you prove this theorem? Please pause the video, identify an appropriate proof technique for this theorem, and go ahead and write down the proof. Okay, so at least one way of proving this theorem is to use a proof by contradiction. We're going to assume the negation of this proposition. So what does it mean to say it is not the case that at least one box contains at least two objects? Well, it means that there are no boxes that contain two or more objects, which means for any box, the maximum number of objects in it is 1. Well, if that's the case and there are k boxes, then the maximum number of objects that you can place into the k boxes is just k. But k is less than n. Therefore, it's impossible to place the n objects into the k boxes if there is at most one object per box. And that's the contradiction because we assume that the n objects fit into the k boxes. So that is the simplest version of the pigeonhole principle. Let's look at an example of an application. So in a class of 30 students, according to the pigeonhole principle, we can infer that at least 2 students were born in the same month. So for example, at least 2 students were born in January, or 2 students were born in February, and so on and so forth. At least one of these propositions must be true. So let's make sure we make it explicit how this example fits the pigeonhole principle. So in this case, the number of students, 30, is equal to n. And the number of months, that is 12, is equal to r. Because what you're trying to do is you're trying to place the students into the boxes or the 12 month of the year. So what the theorem says is if you have 30 students and only 12 months, then you must put at least 2 students in the same box or the same month. So that's an obvious application of this pigeonhole principle. Now it turns out there's a second formulation of this principle that's a little bit more powerful, and we're going to state it as theorem 2. Here it goes. If n objects are placed into k boxes and n is strictly greater than k and both of these integers are positive, then not only at least one box contains at least 2 objects. In fact, at least one box contains this many objects, where this is the ceiling of n over k. So, to illustrate how this theorem works and why it's a little bit more powerful than the first version of the pigeonhole principle, let's look at the first example again. But this time we're going to make a stronger claim. We're going to say in a class of 30 students again, at least 3 students were born in the same month. How do we get the number 3? Well, we use this formula. N is 30, k is 12. So when we divide 30 by 12 and we round up using the ceiling function, then we get the ceiling of 2.5, which is equal to 3. to better understand the difference between these two versions of the pigeonhole principle, and in particular to convince ourselves that this version is more powerful or stronger than this version, let's visualize another concrete example where k is equal to 5 and n is equal to 12. That is, we have 5 distinct boxes and we have 12 distinct objects. So one way to look at these theorems is to consider them as algorithms that take as input the values n and k and then output their final conclusion. So what algorithm would this principle use? Given 12 objects and 5 boxes, how could it go about figuring out that at least one box will contain more than one object? So the first version of the pigeonhole principle could use a very simple iterative algorithm to produce its answer. Each iteration of the loop would consist in simply picking one of the unplaced objects and placing it into an empty box. And the loop would terminate when there are no empty boxes left. So let me trace this algorithm for you. First, in the first iteration, I'm going to pick one unplaced object, and then I'm going to move it into the first empty box. During the second iteration of the loop, I will pick another unplaced object, say this one, and I will move it into the next empty box. Similarly, in the third iteration, I would pick a random unplaced object, say this one, and move it into the next empty box. And so on and so forth with this object next. Here is the next empty box. And in the fifth iteration, I will pick, say, this object, move it into the next empty box. And at the end of the fifth iteration, we notice that there are no empty boxes left. Therefore, the algorithm terminates, and the first version of the pigeonhole principle can already conclude without any extra work that at least one of the boxes is going to contain more than one object, because we still have a lot of unplaced objects to be put into boxes, but there are no empty boxes left. Now let's turn our attention to the second version of the pigeonhole principle, and let's simulate it with a similar algorithm. Now the main difference in this algorithm is that the termination condition is not to stop when there are no empty boxes anymore. It is supposed to stop when there are no unplaced objects at all. So it would also consider the boxes from left to right. In fact, it would behave exactly as the previous algorithm up to now. But here, instead of stopping, it would actually grab a next random object and position it in the leftmost box. Then it will grab the next random object, put it in the second box, and so on and so forth until one of two things happen. Either you reach the end of the row of boxes, or you run out of objects to place into boxes. Now in this case, what happens first is that we've reached the rightmost box again. So instead of stopping again, we're going to keep going. Remember, the termination condition is to stop when there are no more unplaced objects, but here we have two more objects to consider or to place into boxes. So we just reached the last box, so we go back to the first box again, take another unplaced object, put it in the first box, take yet another unplaced object and put it in the next box. And now we stop the algorithm because we have run out of unplaced objects. And the output of the second algorithm is simply the number of objects in the leftmost box, which is 3. So, of course, we don't have to implement any algorithm. This is just to give you an intuition for what these principles actually compute. Of course, in the second case, the easiest way to do it is just to count how many times k goes into n. And if that number is not an integer, you have to round up to the next integer, since it's impossible to put a fraction of an object into a box. You have to put whole objects into boxes. So make sure you understand the reason for this computation, and make sure you understand the difference between these two versions of the pigeonhole principle.